Okay. At the moment, we have seen how to evaluate the expectation value over this later determinant of all the possible terms that we have had in the Hamiltonian. So we may write down a full expression for the expectation value over the Slater determinant when we use the all the terms that we had within the Hamiltonian. We had two one-body operators that were the kinetic one So there was the kinetic term, one body, and the interaction with the ionic potential. Also, that is a one-body operator because we consider just one electron at a time. And then we have the two body contributions. So we have phi k, phi m, then we have E squared divided by r minus r prime, then we have phi k, phi m, and there's also the 4 pi E0 term, and then minus 1/2 summation over k and m of phi k, phi m, E squared divided by r minus r prime, phi m, phi k, and divided by 4 pi E0. So this is the expectation value of the full Hamiltonian over this later determinant that represents the energy of the system. And what may, let's say, if you try to to find the constraint concerning the wave functions that minimize this expression, what one finds is that if you require that this expectation value is minimum, then the condition over the wave functions is the following. So you have that the wave function have to fulfill this equation yeah, I forgot for I0. So what you have is that the wave functions that help to minimize this expectation value have to satisfy a Schrödinger equation where here we have the usual kinetic term, then here we have the interaction with the ions. Then if you notice this term here, what was related with the, let's say, with the direct term, you have a summation. I just rewrite this term here. We have 1/2 sum over m of d3r prime. Then we have the square modulus of the phi m. Then we may divide e squared in minus e times minus e. And if we apply this summation to all the possible wave functions, what we have is that is equal to how did I call last time the total density when I presented the R3 model? Total, okay. Okay. Okay, let me leave P K of R minus C. So this is a sort of interaction between, let's say, one electron and the average density that is produced by the other electrons. So this is something that resembles what we have observed in the Drude picture, in the R3 model, when the contribution of all the electrons could be written in terms of the average density produced by those electrons. And the last term, that is the term that is related to the exchange contribution to the expectation value, cannot be written in the same using the same method, because in this case we have minus 1/2 summation over m of d3r prime. We have phi of m conjugated r prime e squared, and then within the integral there is the with the same coordinate, we have not the m level, but we have the k level. So due to that, let's say it's not possible to write the square modulus, and then we multiply by phi m. If you notice here, this is an equation that, if you consider just the first three terms, is a Schrödinger equation applied to level k. But in the first three terms, here we have the kinetic operator applied to level k. Here we have the product between the ion contribution and level k. Here we have the multiplication between the electron charge density, let's say, and level k. So in these cases, we have a local contribution of level k. So locally in position r, level k gives us the contribution to the Schrödinger equation. But in this case, level k is within the integral. So this term is non-local, as we have to make the integral of level k over all space before being able to evaluate this contribution. So this term is more complicated with respect to the terms we usually found in the Hamiltonians. This resembles somehow the pseudo-potential, because in the pseudo-potential we had the wave function that we tried to use for the evaluation of the energy was within the integral that we used for the definition of the pseudo-potential. So also in this case, the wave function that we want to use as a solution of the Schrödinger equation is within is within one integral. So let's say the evaluation of this term is complicated due to this fact, because that term is actually within the wave function you want to use as a solution is actually within the integral. So in general, it's not easy to use this, let's say, to solve the equation and to find the value of the energy. There is just one situation where this calculation is quite easy. Let's say easy in the sense that the structure of the wave function is not complex, and due to that, let's say you have both some simplifications, and also the evaluation, in particular of the last integral, can be done analytically. And this case is a case that we have already met many times during the lessons, and is the case where we consider only plane waves. So why I took into consideration plane waves? Because the idea is once we have those equations, the idea is to try to estimate what is the intensity of this contribution, just to understand whether the appearance of the exchange term produces just a slight redefinition of the energy of the system, or if we have a strong contribution to the energy itself. And why is that important? Because, for instance, the speed of the electrons is related to the gradient of the energy. So the energy, as we saw during the evaluation, the application of the semi-classical model in presence of external fields is an important quantity that we need to refer to when trying to understand, for instance, the dynamical properties of the system, or the energy of the electrons, the velocity of the electrons, and so on. So due to that, it's important to estimate the contribution to the exchange integral to the overall, to the energy of the system. Again, just to understand whether that introduces a slight modification or a strong contribution to the total energy of the system. So if we may expect to have strong deformations of the results we have obtained up to now due to the presence of this integral, or if we may still use all the approximations and conclusions we have obtained up to now. So in this case, it's using plane waves, it's possible to make an estimate, just because, again, plane waves are quite simple. So as they have a very simple structure. And the contribution to the integral, the use of plane waves to this evaluation, it's let's say, simplifies the problem, also not just due to the structure of the wave function, that is just a phase, but also due to another motivation. Because if we use plane waves, we may, let's say, recall what was used in the Sommerfeld picture, because actually plane waves are the solution when the system is, when you consider that the contribution coming from the ions is not localized, as we have discussed up to now, but the charge density of the ions is supposed to be uniform. So you do not have, let's say, you may have a periodic potential in the system, but that periodic potential is equal to 0. So at this point, with this in mind, what may we say concerning this contribution? So the interaction with the ions and these contributions, so the interaction with all the electrons. Due to the fact that we have to maintain charge neutrality, the overall charge due to the ions is exactly equal to the overall charge due to the electrons. So in this term here, you consider the interaction between one electron and the uniform background of charge that is due to ions. On the other side, in the second term, you consider the interaction between one electron and the uniform background of charge, because due to the fact that you use plane waves, the background of charge of each electron is uniform over the system. So in this case, we have this interaction with the uniform background of charge due to all the other electrons, but the amount of charge that we have in the first term in the case of ions and the amount of charge that we have in the second term in case of electrons are exactly the same, apart from the sign. So we have a negative contribution coming from the interaction with the ions, a positive contribution coming from the interaction with the electrons, but those two contributions are expected to be exactly the same, because the amount of negative charge in the system and positive charge in the system is equal, again, because we have charge neutrality. So the final point of the discussion is, when we consider the when we use plane waves to evaluate the contribution of the exchange energy, we may simplify the initial equation, that is this equation here, by keeping just two terms. One term is the kinetic one, so minus h bar squared divided by 2m. Then we have the gradient of phi k. Then we may neglect the interaction with the ions and the interaction with the electrons, because they are expected to give us the same contribution, and we may just keep minus the exchange term, so the summation over m of d3 r prime phi m r prime e squared r minus r prime phi k r prime phi m of r. So to evaluate the energy corresponding to this to level k, let's say. And please note that also in this situation, we are using plane waves that are a solution to the Schrödinger problem, where the potential contribution is zero. So the plane waves in principle are the solution when just the kinetic term is there. We use plane waves to evaluate the effect of the exchange term, so the modification of the energy on the energy due to the presence of this second contribution. So somehow we are transferring the effect of the interaction from a modification to the wave function to a modification of the energy. So also here we are using electronic levels that are one electron levels. So the multi-electron behavior has completely disappeared. So this later determinant doesn't appear in this equation. So we have just one level wave functions here, one electron wave function, as we used up to now before discussing the electron-electron interaction. So the effect of the mutual interaction between the electrons will be included just in the value of Ek. So we will have a final value of Ek that is not the free electron value. So at the end, we keep exactly the same picture that we had before. We just, let's say, rescale the energy and include in this rescaling the effect of the interaction. So we are somehow going on with the, let's say, single electron picture for what concerns the levels, and we have transferred the effect of interaction only on the energy, so only on this scalar term that can be associated to the levels. So what I would like to do now is just to start the calculation. And why I say I would like just to start, not because I don't want to conclude that, but because the calculation is quite long. So I will make all the steps of the calculations just to the point where from that point on you have just some let's say there's no more physics in those steps. There's just a modification of the terms to find the closed expression that I present you at the end of the calculation. So I think that I will not be able to make in these 20 minutes the full detailed calculation. So I just, let's say, I don't get the term in English, imposto il calcolo in italiano. I conclude this discussion in Italian. Imposto il calcolo in italiano, arrivo fino al momento in cui, diciamo così, vengono fatti i passaggi principali e poi da lì in avanti è solo questione di modificare l'espressione tenendo conto delle varie condizioni e arrivare al punto finale, solo che pur essendo una parte poco complessa è lunga e quindi la salto e vado direttamente poi al risultato finale. Okay. Okay, so, oops. So the equation is no. Okay. So in this case, phi k of r is 1 divided by the square root of the volume e to the I k r, and phi m will be 1 divided by the square root of the volume e to the I m scalar product r. So in the first case, we have just the free electron value. So we have h bar squared k squared divided by twice the electronic mass. Then we have 1 divided by the square root of the volume e to the I k r. Then we have minus the summation over m of d3r prime. This is e to the minus I m r prime. Then we have e to the I k r prime divided by r minus r prime. Then we have e squared divided by 4 pi e0, then e to the I m r, and this is equal to up. And here we have a square root of the volume below this wave function, and then we have a volume here because we have two phases. So we have the square root coming from the first one, square root from the second one, so we have just v. On the other side, we have the energy of k times 1 divided by the square root of the volume e to the I k r. So we may remove the square roots of the volume 1, 2, and 3. So we just keep the volume that is within the integral. Then we may also simplify the phase corresponding to wave vector k. But when we do that, since the phase with wave vector k is within the integral, we may not simplify with this phase here. A new phase appears here with the k wave vector and the r coordinate. So what we have is h bar squared k squared divided by twice the electronic mass minus the summation over m of 1 divided by the volume. Then we have the integral of d3 r prime, and we have e to the minus I m r prime, e to the I k r prime. Then we have e to the I m r and e to the minus I k r. That comes from the simplification of the phase. Then we have r minus r prime. Then there is the square of the electronic charge divided by 4 pi E0, and this is equal to Ek. Due to the fact that the only term we may need to consider is this one here, because the first one is just the free electron value. So to evaluate the final value of Ek, we just need to compute this term. I just focus on that. And if you don't mind, I also, let's say, keep out of the, let's say, for the moment, I forget E0 and also forget E squared. I will keep the 4 pi because the 4 pi will be used later for a simplification. But for the moment, I just concentrate on the evaluation of the summation over m of 1 divided by the volume d3 r prime e to the minus I m r prime e to the I k r prime e to the I m r e to the minus I k r, and then divided by r minus r prime, and also divided by 4 pi. So I just concentrate on that, and I E squared divided by E0 are a coefficient that will be in front of this term here, and I will just rejoin that at the end of the calculation. Now, if you notice the 4 phases, we have m, index m with r and r prime, and index k with r and r prime. So just looking at the phases, I may collect m. So I have I m, then I have r minus r prime. I may also collect Ik, and I have r prime minus r if I collect k. At this point, I may collect r minus r prime. So what I have here is the imaginary unit is in front of here, then I have r minus r prime, and then I have m minus k. So taking into consideration this simplification, we have minus sum over m1 divided by the volume, then d3 r prime divided by 4 pi, then e to the I m minus k r minus r prime divided by r minus r prime. Due to the fact that here we have an integral over r prime, if we just make a translation of the coordinate of integration, we may just replace r minus r prime with r prime. So now I just make this, let's say, modification, translation over the variable of integration. So what we have here at the end is minus a summation over m of 1 divided by v, d3 r prime divided by 4 pi e to the I m minus k r prime divided by the modulus of r prime. Okay, and at this point, this is let's say the function that we have, the function of r prime that we have here is 1 divided by r prime. Then we have an integral over the full space of the 3r prime this function times a phase corresponding to the wave vector m minus k. So this can be considered to be the Fourier transform of the 1 divided by r prime function corresponding to wave vector m minus k. So this can be written as a summation over m of 1 divided by the volume and the Fourier transform of 1 over r corresponding to wave vector q is a 4 pi divided by q squared. So in this case, the 4 pi is included in the, let's say, definition of the Fourier transform. So what I have left here is just 1 divided by m minus k squared. So we just end up with the evaluation of this sum. And yeah, from I just squared. So remember the power of two here. Now I just give you an indication of how to go on with this integral, and then I give you directly the solution. Oggi. So the idea to reach the solution is the following. This M runs over all the possible levels we have in the system. So since we are considering plane waves, we have to consider all the possible indexes that are found within the Fermi sphere. So this is a summation over all the possible levels that we have within the Fermi sphere. At this point, we may transform this into an integral. So we have 1 divided by V, the volume, then we have the integral over d3m. The volume element is 2 pi to the power of 3 divided by the volume, and then we have m minus k squared. At this point, the volume may be simplified, and the integral is over the Fermi sphere. We may use the fact that we may transform the integral into we may change from Cartesian coordinates to spherical coordinates, and so in this case we have the integral over the m squared sin theta d theta d phi. Then we have 1 divided by the m minus k squared. M minus k squared can be written as m squared plus k squared minus 2 times m scalar product k. Now, the variable of integration here is m. So if we take, if we choose let's say, the orientation of the z-axis when we define the polar coordinates such that the z-axis is along k. So if the z-axis in the polar components is parallel to k, then this scalar product m scalar k can be written just in terms of the cosine of the angle theta, that is the angle in the spherical coordinates that is evaluated with respect to the z-axis. So due to that, I may write this scalar product as m modulus k modulus cosine of theta. So in this case, I use the variable theta, that is the angle respect to the z-axis, to evaluate the scalar product with the in between m and k. And then I rewrite the volume element in corresponding to theta as minus d cos theta. So I change variable from theta to cos theta, and in this way, then the, let's say, the integral over the phi angle gives just 2 pi, because nothing depends on phi in this integral. And so due to those simplifications, it's possible to, let's say, go on with the integral. In particular, here you may exploit the logarithm function to solve the integral related to this fraction here, because m squared is the let's say, before making the integral over m, you make the integral over theta, or sorry, over d cos theta, you have a constant plus a constant minus twice a constant that multiplies the variable. So it's just like as if 1 divided by a minus b times the variable of integration. And the primitive of that is a logarithm. So by making first the integral over theta and then the integral over m, then you may solve the full integration. But let's say it's quite a long procedure. So due to that, I just wanted to give you the first indication of how to solve that, and then just give you the final solution. And the final solution is the following. So we have h bar squared divided by twice the mass times k squared, that is just the, again, the free electron value. Then we have minus 2 e squared divided by pi times the kf, so the wave vector corresponding to the Fermi surface, times a function f that is a function of k divided by kf. The expression of f is the following. So we have 1/2 plus 1 minus x squared divided by 4x times the logarithm of the modulus of 1 plus x divided by 1 minus x. Before, let's say, next week, I will discuss what happens due to this function. At this point, since we are quite close to the end of the lesson, I would just like to discuss with you about this expression. So this is the energy corresponding to the this is the energy corresponding to one level. So level K has an energy that is given by this expression. We may try to evaluate the total energy. So we may try to find the sum of Ek times 2, because every level may host 2 electrons. And the integral of the first part was we did that when we consider the Sommerfeld model. So in this case, the energy is the average energy is for each electron is 3 divided by 5 times EF. So the total energy due to the first component is just n times 3 divided by 5 EF, where n is the number of electrons. The second term gives an overall value that is minus n times 3 divided by 4 E squared kf divided pi squared E0. So in this, just to understand what is the relationship between those two terms, it's useful to use a parameter that is presented in the textbook, that is the following. If you suppose that one electron, so if this is one electron, and if you suppose that that electron occupies a spherical volume where just that electron is found, and if you call R0 the radius of that sphere, then you may write the density as 1 divided by the volume of that sphere. Because if we associate on average to each electron a spherical volume with radius R0, then the density of electron is the reciprocal of that. So R0 is an estimate of the average electron-electron distance. If you remember, we noticed that Kf to the power of 3 is equal to 3 pi square density. So there is a connection between Kf and R0. In particular, if we also express so if we also express EF using Kf, at this point we have a Kf squared here and the Kf in the second term. So if Kf squared is proportional to the electronic density to the power of 2 divided by 3, because Kf is proportional to the cubic root of the density. So this is proportional to 1 divided by R0 to the power of 2, because the density is inversely proportional with the cubic power of R0. For the same motivation, Kf is proportional to 1 divided by R0. So we expect that the first term scales as 1 divided by R0 squared, and the second term scales as 1 divided by R0. If you make all the calculations, write down h bar, the value of h bar, electronic mass, electronic charge, and so on, you find this expression that is 13.5 eV divided by R0 expressed in angstroms minus 6.6 eV divided by R0 expressed in angstroms. When I say expressed in angstroms, I mean that R0 in this expression is just a number. So no unit of measurements. If you have to set there 3 angstroms, just put 3, because I have already taken into consideration the unit of measurement of R0 when evaluating the EV. So here R0 is just a number. And just to plot that, and then I stop the lesson. Just to plot that, you have that if we make a plot of the energy as a function of R0, we have that the kinetic term is positive, and this like this. The potential term, the exchange term, is negative and is like this. Due to the fact that when we are close to zero, the term that is larger is the kinetic one. The final dependence will start from here, so from positive values, then the dependence comes down, goes to negative values, and then we approach zero. So at low values of R0, the dominating term is the kinetic one, then the prevailing term is the exchange one, and then at the end, for large values of R0, they both go to zero. So the idea is that the exchange term is not the dominating one when R0 is small. When R0 is small, the dominating term is the kinetic. So and this is a bit counterintuitive, because if you have a contribution coming from the interaction, then you expect that the contribution of the interaction is larger when the distance is smaller, because you have the possibility to have a strong interaction. But this graph tells us that this is not the picture, because the main contribution of R0 appears when R0 is not the smallest possible value, but so we have not the highest possible density, but that term has a contribution when the density is slightly smaller than the large density case. And what is the motivation of that? The motivation of that is if you closely pack the system, if you remember the case of the tie binding model, what happens when the superposition is strong? The width of the band increases, but that increase is due to kinetic energy. So that is to say, if you try to compress the electron in a small volume, then the spread of the energy levels increases. So the more you try to confine the electron, the larger will be the energy levels that you have. So if you increase the density too much, if the average distance between the electrons is very small, then the dominating term is the kinetic due to the localization of the electron. Differently, if you decrease slightly the density, so at this point the kinetic contribution is lower, so you have less effect coming just from the localization, then you may observe the actual value of the interaction term, let's say, that is the exchange term. So the contribution of that is more pronounced here at slightly larger values of R0 or slightly smaller density with respect to what one could imagine for, let's say, very small values of R0 or larger and larger densities. So the final point is we actually have a contribution from the exchange term, and next time we will evaluate that in detail. And that contribution is not observed when the electrons are very, very densely packed, because at that point the kinetic term prevails. So the density has to be slightly larger than that, and at that point it's possible to observe the contribution of the exchange term. Okay, so do you have questions or comments about this part?
thanks.
Okay, so now I switch off the registration